Hi, thank you very much. Welcome again to my YouTube channel. As usual, do not forget to subscribe, do not forget to comment, do not forget to share. So for now, I want us to see the oscillating system. Basically, we are going to look at the spring mass system, whether it performs simple harmonic motion or not. In other words, we want to show whether this is an oscillating system of the mass and the spring. Do they perform simple harmonic motion? So let us look at this. If I have a spring and this spring is hanging, it's hanging like that, and then I bring in, this is a spring which is just hanging, we have not attached any mass. So we are going to attach because we are looking at the spring mass system. This is our mass. We have attached it here. So the mass will act each way will act vertical downwards, so that is mg. And this is the mass actually. This is the spring. Here, this way, we shall have the tension force acting towards the equilibrium position, and of course, we shall have an extension. The moment you are touching mass down here, there will be an extension that will be caused. Let me say, I will have this and that. So this actually ideally to be is the extension being produced. And then, if we are to see that if we are to prove that this actually performs simple harmonic motion, what we're going to do is we are going to put the mass vertically downwards, slightly vertically downwards. Displace it furthermore below the equilibrium position by a small distance x. Let's say we have this, I have this, still the same spring, but this time we are going to give it a displacement downwards. So this one shall have this, and this is mg. So in this case, we shall have this is another displacement x. We have actually pulled it downwards to give this. So of course, this one is still in, okay? That's the original length. So still here, we shall have the tension, by the tension this time is different. We shall call it T prime. So I am going to call this point 1. And then I will have this as point what? Point 2. Okay? Point 2, rather. This is point 2. So at this point 1, we shall have at equilibrium at point 1, let me call it stage 1 of the spring. We call it stage 1. So at stage 1, we shall have an equilibrium. We shall have that the tension force T is equal to mg. T is equal to mg in this case. That's what we have. But remember, this spring has a force constant, which we call it a spring force constant, K. T has a force constant, K. But we have that the tension T is actually direct because the spring itself obeys Hooke's law. So it is directly proportional to the extension that is being produced, implying that tension T is equal to Ke, where this Ke, actually K is the spring, where K is the spring constant, the spring force constant, like that. So therefore, when you look at this, you'll see that I can call this is 1, call this is 2. when you look at 1 and 2, from 1 and 2, it implies that actually mg is equal to ke. Can call this equation number 3. This is true from the 2. When I come to stage 2, the spring has been displaced furthermore below the equilibrium position by a distance x. So this time round, the tension, the tension is different. So we shall have that at equilibrium. We shall have T prime is equal to mg. That is at this point. But here we shall have that our T prime here now. But then T prime is directly proportional to E plus X. So this implies that our T prime becomes K E plus X in this case. Therefore, we can get the restoring force back to the equilibrium point. So, restoring force towards the equilibrium position. We shall have that force, that restoring force, is equal to a negative. When you look at this, when you pull this, the force goes back. So this tension is more than mg. So we shall have T complement minus mg. Okay? So the restoring force x is 0. That's what we are saying here. T prime is equal to mg. So the way is T prime minus mg gives you 0. It restores. So we shall have F will be ideally mg minus T prime if I open this bracket. But then T prime is here. You can replace it. Therefore, F is equal to mg minus open the bracket. Allow K first. Open the bracket E my plus X like that. So in this case, but we know that mg is equal to ke. This is from equation 3. That is from equation 3. That's when we shall have this. So I replace for mg back here. So therefore, I'll have f is equal to ke minus k, open bracket, e plus x. I am going to open out this, and therefore I'll have that f is going to be ke minus ke, then minus kx alone again. So here you see ke and ke cancel themselves. Therefore, f is equal to negative kx. But from Newton's second law, we shall have that F is equal to mn. So that implies that our mn is equal to negative k what? Kx. So I divide by m, I divide here by n. So therefore, a alone becomes negative of k out of m times x, which is actually in the form, which is in the form a equal to negative omega squared x, which is, you can see that your omega squared is a out of m, the negative is there, your x is there. So that implies that the spring mass system actually obeys or portrays, or as what we call simple, performs. It performs simple harmonic motion. So in this case, we can as well go ahead and get a period for that spring mass system. So we know that where we have omega squared is actually k out of m. So omega alone becomes k over m, but under a root. So period t is equal to 2 pi out of omega. So this one becomes 2 pi. We have this is 2 pi out of the omega, which is the root of k out of m. That is my period, which can be written that the t itself, which is the period, will be written as 2 pi times the root of m over k. So this is the period for the spring mass system that oscillates with simple harmonic motion. If you are to get its frequency, so the frequency can as well be got. Frequency f is 1 out of t. It's the reciprocal of this. So therefore, that implies that our period f becomes 1 out of 2 pi, and then I get the root of k over m. This is the frequency for the spring mass system that oscillates with simple harmonic motion. Thank you very much. Thanks for following.